Okay, in section 5.3, we're going to be talking about trigonometric graphs. We're going to start with sine and cosine. Suppose I want to look at y equal the sine of x. So what I'll do, I'll create a table. I'm not going to pick all the values, but I'm going to pick some easy values. So at 0, when x equals 0, when x is 45 degrees, or pi over 4, because we need to be in radians for this to work, pi over 2, 3 pi over 4, and pi, and the list goes on. But sine of 0 we know is 0. Sine of pi over 4 is radical 2 over 2. If I substitute that in my calculator, that's a 0.7 about. Pi over 2, sine of pi over 2 is 1. 3 pi over 4 is in the second quadrant, and in the second quadrant sine is positive, so it's also radical 2 over 2, which is about 0.7, and sine of pi is 0. If I put this on a number line, 0, 0, and if I am to say that this is pi over 4, pi over 2, 3 pi over 4, and pi, at 0 I am at 0, at pi over 4, and let's say this is 1. I am at 0.7, about right there. At pi over 2 I am at 1. A smooth curve. At 3 pi over 4 I am at 0.7 again. At pi I am at 0. Now if I continue on, if I am to move, and let me use a different color for different values of x, if I am to go with 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Well, along with those, at 5 pi over 4, I know in this quadrant sine is negative, and it's radical 2 over 2, 0.7. 3 pi over 2, I know that's a negative 1. 7 pi over 4, that would be a negative 0.7, and at 2 pi we are at 0. So if I run 4 more values, pi over 4, 2, 3, 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4 reduced. So here I am at about negative 0.7, negative 1, negative about 0.7, and 0. If I continue this graph, again, as smooth as possible. So the graph really looks something like this. If I am to make this a bit thicker and make this as smooth as I can, that's really how the graph looks like somewhat. This is one full cycle. Now, of course, we don't have to label all of these points on it. We do have to label 5 main points. But this is what to remember. If I'm looking at a graph of a sine wave, a graph of a sine runs between y equal 1 and y equal negative 1. And I should remember it starts at the origin. Versus if I run for a graph of y equal cosine, I'm not going to pick points, but similarly, y equal cosine of x, well, this is what I remember. If I wanted to test the same points, I'll notice that the values are very close to what we just got, except at 0, cosine is 1. At pi over 4, it's 0.7. So, in quadrant 2, it's negative. It's about right there. So the graph pretty much looks like this. Now again, the main points that I'm after, the main points that we have to label in all of these graphs are the following. I need to know where does this graph touch the amplitudes, that's what we call those, and the x-axis. And if I look at this graph again, if this is 1 and -1, so unlike sine, cosine starts at the amplitude and runs down to the amplitude and back to the starting point. And the main points that I want label, this x value, this x value, this x value, this x value, and this x value. I need those 5 points labeled. And we're going to go over how to do that. I could use algebra for the shifting and compressing and stretching, but Trig seems to have their own rule, and it's a pretty good one. Otherwise, I would have just used what you learned in your Math 3 from graphing and proceeded that way. So, here we are. If I'm looking at y equal, I'm talking about a sine or cosine, it doesn't matter. The amplitude is the absolute value of the number that's being multiplied by a metric function. The period, that is, how long does it take it to make a full cycle, is 2 pi divided by whatever this number is. I'll elaborate on that in a minute. The shift, there is a phase shift. Take this, set it equal to 0, and solve. And a vertical shift would be the number that's loose by itself, and in trig we only have reflections, nothing more. You reflect with respect to the x-axis, that's about it. So if I was to say sketch a graph of y equal x squared, hopefully we all know how to graph that. Just to demonstrate how this is working, y equal x squared is a graph that looks like this. 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. If I say sketch a graph of y equal, if I was to say 3x minus 2 squared plus 1. Now, wouldn't you say that this is going to shift the graph 2 units to the right? This is going to shift the graph 2 units to the right. That's when you set this equal to 0 and solve it. And wouldn't you go up 1 unit? A vertical shift is the number that's loose by itself. And doesn't this compress the graph by a factor of 3? Well, here the amplitude takes care of that. That's the beauty of this. And here there's no period, but in those we have a full period. A graph of a sine or cosine never terminates. It continues on. One cycle would be between 0 and 2 pi if we're talking about the sine or cosine of a function. But these graphs are infinite. They never stop. And they never terminate. So let's start with this. If I eyeball those 5 things that they want, provided where they exist, and I start graphing again, I could use algebra. I'm not going to use algebra, I'm going to use trig, because trig has a much easier way of really sketching those and labeling. So 5 things I need at most. I glance at a problem, and this is the worst case scenario. I have all of these things happening. If I look at number 2, I notice there's only one of those. That's it. 1. The amplitude is 2. The period is always 2 pi divided by the number in front of x. Well, there's nothing in front of x, so it's 2 pi. So the way it's going to work, I'll get my grid. Remember, I could scale this any way I want. So I'm going to always scale 4 pieces. If I look at this, I start with my, when I sketched the graph of this, what did we do first? Did you notice when I graphed this, first I shifted 2 to the right, then 1 up, then I sketched the graph. So normally we tackle those first. Then we use the amplitude to figure out how high or low the graph runs. Then we sketch a graph, and the last thing we do is we label. That's the order we do things in. So let me glance at this problem and apply this. Actually, I do that in every problem. Well, y equal to 1, 2. Actually, 1, 2, 1, 2. That would be the amplitude. I would sketch that. The reason I'm starting with the amplitude, there are no shifts. So 1 is done, I went to 2 straight. Now what? A graph of a sine wave, I just realized it starts at the origin, and I always break it into the 4 parts that I need. Always. It's going to run up to the amplitude, and my graph will look like this regardless. It's the labeling that's going to make a big difference. So, one thing about the graph of a sine or cosine, those are equidistant. All of these are equal. And here, all of these are also equal. Always. So, when I look at the main points that I need to label, and I need to label where does the graph cross the x-axis, and where does the graph hit the amplitudes. Those are always equidistant. And since there are 1, 2, 3, 4 of them, it would be best to figure out what this is. And since there's 4 parts, take the period and divide it by 4. And like I said in this class, since we are always dealing with fractions, it's best not to divide by 4, rather to multiply by a fourth. That's pi over 2. This tells me this is 1 pi over 2, and you're just adding fractions. 2 pi over 2, 3 pi over 2, 4 pi over 2. If I was to ask you to sketch another period, and I will, you could continue the same trend and give me as many periods as I like. If you start with pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 6 pi over 2, 7 pi over 2, and 8 pi over 2 is 4 pi. If you decided to give me a period to the left, to the right you add, to the left you subtract. It's not that challenging. So this is, to the right you went negative pi over 2, positive pi over 2, to the left negative pi over 2, negative 2 pi over 2, negative 3 pi over 2, and negative 4 pi over 2. I ask for 2 periods. In general, I want you to go to the starting point, and I want you to sketch the first period. Either I'm going to ask you for another period to the right or to the left. I messed up. This period I extended, oops, I overextended that. That's one period, my mistake. The second period starts right there. So I ask for 2 periods, either to the right or to the left. It doesn't matter. Sometimes I say 2 to the right. Sometimes I say 1 to the right, 1 to the left. When I look at this problem, amplitude is 1. Okay, it's the number in front of the trig function. 2, the period is 2 pi divided by this number, which is pi. This graph is compressed. Now remember, you could graph it anywhere you want, and I'm going to graph them all. They're going to look identical. Graphing is the easy part. Labeling is the challenging part. So I start with 1, y equal 1. And I label that clearly, because this guy is really picky. And y equal negative 1. And a graph of a sine, again, starts at the origin, runs up to the amplitude, back to the starting point. I just need the first cycle out, and I'm in good shape. And if I remember correctly, I have to label wherever those coordinates on the x-axis match. Where does the graph cross the amplitude and the x-axis? Well, let's see how this works. If I really keep on playing this game of 1/4, because I know this equal to this, equal to this, equal to this. Those four chunks are equal. This, 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 and this. All of these are equal. So, since there's four of them, if I take the period and I divide it by 4, or 1/4 of the period, that's pi over 4. That tells me what this point is. That is pi over 4, 2 pi over 4. If you reduce it, 3 pi over 4, and 4 pi over 4, which is pi. If I was to ask you to sketch a period to the right and a period to the left, well, to the left, you just mimic that graph. To the right, it was pi over 4. To the left, negative pi over 4, negative 2 pi over 4, negative 3 pi over 4, and negative 4 pi over 4. And that will be 2 complete cycles. And that's all I would want. One more before I conclude this video and move to the next. Well, how about this one? Here, the amplitude is 3. 2, the period is 2 pi divided by 5. Got it. The graph is the easy part. Labeling is the tough part. Remember, I can scale this any way I want. I need to go up to 3. So I'm going to say this is 1, this is 2, this is 3. As long as you label it, it makes no difference. And there it is. Now it's official. 1, 2, 3. And if I was to say, let's sketch a graph, let's go by a cosine. A cosine starts on the amplitude. And since I have a grid of those rectangles, I make use of them. And there's the graph. Now what? Now comes the tough part. Labeling is more important than the graph. And we're going to find the labeling without graphing in chapter 7 when we solve equations. How am I going to figure what those points are? Well, that's easy. This point right here is always 1/4 of the period. And that's the key. And if you read the book, I know the book doesn't do that, but believe me, it will worth your while to do this. That's pi over 10. Once I establish that this is 1 pi over 10, this is 2 pi over 10. This is 3 pi over 10. And this is 4 pi over 10. And if I was to ask for another period, let's say this time to the right. Another full cycle to the right. Again, the graphing, you can graph as many of those as you like. That's really easy. Labeling is a different story. Well, I started with 1 pi over 10, 2 pi over 10, 3 pi over 10, 4 pi over 10, 5 pi over 10, 6 pi over 10, 7 pi over 10, and 8 pi over 10. Right? 8 pi over 10. I'm reducing those. Okay, I'm gonna stop here now and I'll pick this up in the next video.